Hello, everyone. This is Yogeshwar. Um, it's 3 o'clock, so we'll wait another minute or so to get our week 5 seminar series talk started. Am I audible?
Yes.
Okay, nice. All right, I think we can get started now. Welcome, everyone. In today's talk, we will be covering classification. I know we had covered some of the classification techniques, like the decision tree algorithm in one of the previous lectures, but we will try to also include that and have some hands-on um, activity wherein we will cover um, how to model, how to do the feature training, and um, run a couple of classification algorithms and do the prediction. Also, we will be looking into how we can visualize some of the classification techniques, and also talk about some of the homework assignment for you all to try out. So I think let's get started. So for classification, which is supervised learning technique. So as we had covered regression techniques in the previous classes. So in the regression technique, we had um, a specific discrete output that we were predicting based on a couple of inputs. And in the classification technique, what we have is like, we have a subset, we have a data set, and the data set could be classified into a couple of categories, and based on that, we can predict whether this data set or this data point entry belongs to a certain class or not. Let's look more into classification based on a running example over here. So the running example for today's class is based on this data set called Iris flower data set. So in Iris flower data set, what we have is um, we have a flower over here which belongs to 3 kind of categories. So one of them is Setiusa, versicolor, and virginica. So um, if you just skim through it, they look almost the same, but if you observe minutely, then the distinct features over here is the petal and the sepal that you see. So for each of these categories, the features, the petal and the sepal, they have a different dimensions associated for each of these categories. So um, based on that, we can perhaps say that whether a given flower fits in either of these categories. So that would be some like a classification problem wherein you are given an unknown flower with a given set of a length or a width of a petal or a sepal, and you have to identify to which category does this flower would belong to. So that will be a classification task, and let's try to look into uh, how the data set might look like. So the data set for this iris flower data set is we have the input feature set, which, as you can see, is represented by X, and individual columns, they represent the different feature types associated with that flower. So you have the length, the sepal length, the width, the petal length, the width. So these are the 4 columns. Uh, and then we also have the labels for each of these. So the first row, the flower category, it belongs to the Setosa. For the second row, the flower category again belongs to Setosa, and so on and so forth. So we have the length of the like the dimensions of the flower, and then we categorize whether it belongs to what kind of class of the flower category, whether it is Setosa, versicolor, or virginica. So that's the input data set that we have with us. And again, this classification is a supervised technique. So what we have is the data set has the input features as well as the output features. So output feature over here is the kind of category it belongs to. And the input feature over here would be the individual columns that we see in the X block here. But if we are talking about unsupervised machine learning technique, then we won't have the Y labels associated with it. We will be only provided with X. So that's just a recap of what is like supervised and then unsupervised with respect to this example here. So there are different kinds of classifier algorithms that are available. And if we look at the scikit library that we'll be using, it also supports the different kinds of classifiers. So we have the decision tree, one of which we had seen in the previous exam, one of the previous classes. Then we have artificial neural network, support vector machine, k-nearest neighbor. We also have something called as an ensemble methods. So that in these category of methods, we have like random forest, bagging, and AdaBoost. And in one of our previous classes, we also saw a use case wherein Peter demonstrated how he used one of these classifiers, ensemble methods, in his particular use case. Let's, at a high level, let's briefly cover one type of classifier, which is the KNN. KNN stands for nearest neighbor classification. So in this classification technique, what we do is we have these X1 and X2, which are the 2 features, and the red, the triangle, and the plus, they basically depict 3 different categories that we have. So the input data set consists of 2 features. So it has X1 and X2. So these would be the 2 columns of an X matrix. And on the Y, we have 3 different kinds of categories. So the categories over here would be a triangle, which is denoted by the blue color triangle over here. We have another category, which is denoted by a circle, the red circle. And then we have a plus, which is another kind of category. Now, the task over here is if we have an input, which is denoted by this question mark, which basically is a coordinate which has X1 and X2 as an values, then we would like to identify to what category does this input value belongs to. So we have to identify whether it belongs to a class of circle, whether it belongs to a class of triangle, whether it belongs to a class of a plus sign. right? So that is the task that we have to do. So in nearest neighbor algorithm, the gist of that is what it does is it tries to find out k number of neighbors which are very close to this particular point. The point over here of interest is this question mark point. So what it does is it tries to identify who are the neighbors that it has, okay? And based on, so in this circle over here, we see that there are three triangles, one circle and one positive. So when it takes a distance and distance measure and it tries to find out which are the closest points around it, then when it finds for a given distance over here, we have these different classes that we identified, right? So we have three triangles and so on, right? So what it does is it identifies what are the majority of points that are nearest to it. So in this particular example, the majority of points or the categories that are closest to this question mark belongs to triangle. So this algorithm does the majority voting and identifies which is the category that it may belong to. So it predicts that since the majority of points around itself is a triangle, then the prediction is a triangle. So that's how it categorizes that it belongs to a triangle category. Now the distance over here, you can see that it just takes a Euclidean distance, but there are different formats for how to measure the distance. There is something called Manhattan distance, Euclidean distance, and there are different other formulas that are associated with finding out this distance measure. One of the important things that that is recommended is whenever you choose the value of this k, it should be chosen in an odd format so that there is no so there is always some majority over the other. So if you choose like 2, for instance, then you may have like 2 neighbors which are closest to this question mark, and one neighbor may be a triangle and another neighbor could be a circle, and over here there won't be any majority because the k equals 2. So so to avoid that kind of scenarios, you always the best practice is to always use k, which is an odd value. So that's the k nearest neighbor classification algorithm. The other category of classification algorithm is a decision tree. So
do you mind me saying something quick about the number of neighbors?
Sure, Brian.
So if you're doing binary classification, it certainly is it's certainly having an odd number of neighbors would be sufficient, but I think you usually want them to be a prime number, not divisible by the number of classes or outcomes. Does that make sense?
Yes. Okay.
It doesn't. Yeah. It really just matters that it's not divisible. Like you basically just want to avoid ties.
Right. Yeah, sorry. I mean, definitely, those are good points, and those are some of the best practices that are in the literature. Like, how do you figure out a value of k? So again, the k. So one of the disadvantages of this KNN is the user has to decide what should be the value of k. So that is, so you can set whatever the value of k that you want, but based on the value of k, your accuracy of the predictions may also differ. So how to figure out the best value of k is also a challenge for this nearest neighbor classification.
It's Peter. Also, there is a, I probably missed the first few minutes, but there is a huge disadvantage of k nearest neighbors for large data sets, because you are not building a model, right? So your model is the entire data set. So when you do the predictions, you have to carry and you have to consider your entire training set all the time. You are not, since you are not distilling a nice model with parameters from it. You have to consider and you have to carry all your training data set for the prediction phase.
Yes. So yeah, one of the things with the k nearest neighbor is, since we are basing this based on the distance, if you have more features, that means you'll have more dimensions, and the calculation of that, the computation cost can be very large, and hence building that model would probably also be computationally intensive. So does that address some of the points, Peter?
Yeah.
Yeah, nice. Yes, so another classification is the decision tree. So in one of the previous class, we did talk about decision tree regression. In this decision tree classification, basically you keep on building a decision tree based on the features. So for this particular example, then we could have something like a petal length, and the petal length, you could say that is the distance or the length of the petal less than 2.5. If it is yes, then it belongs to a certain category. If no, then we keep on building up this decision tree internally, and we come up to a category. Like if we satisfy those conditions, then what category do that input data set belongs to? It could. So in this example, we see that the category, the decision tree just uses the petal length, but there are other features also that also can go into this decision tree, which is not considered for this specific example over here. So decision tree is another kind of classifier, which is also commonly used to do the classification and categorization of the input data. I just wanted to briefly cover the linear regression. So in linear regression, before I move into something called as logistic regression. So in linear regression, what we have is, if we look at the linear regression problems, then we have the X and Y axis, and we kind of predict what would be the value of Y given an X as an input, right? So in that, in this, basically, this is how the architecture will look like. So we have the X, and then we have the coefficients or the weight for each of the input features. And based on that, we calculate the predicted output. So if you remember when we were talking about finding the price of a house, then we use the input data set, which comprise something like the lot size, the lot size, and I think there were other features that we took into account. And based on that, we were calculating what would be the price of that house, right? So the output over there was the price. But what if we could use this to identify what kind of house that is? So again, if we still use the same input data set, which is like the lot size, the number of stories that the house has, then we could potentially also classify what kind of house it is, whether it's a house, whether it's a townhouse, whether it's a condo, and so on and so forth, right? So that would be the classification. And the reason I brought linear regression over here is we just have a distinct value that we predict over here. In logistic regression, which is a kind of an extension of linear regression, what we have is the output that is generated from that is passed through logit or a sigmoid function, which basically identifies whether, so for instance, whether the output is 0 or 1. So if we say the house is a townhouse or a regular house, then based on the input features that we have, it can classify whether it is a townhouse as 0 or if it is a regular house as 1. So over here we would have a distinct, the category would be based on whether it's a 0 or 1. And not necessarily the price that we saw previously in a regression kind of problems. So even though there is a regression in this name for the logistic regression, it actually does a classification task. Yeah, so we covered decision trees, the KNN, logistic regression. There are as well other regression classification types, such as like neural network and what else? Like the neural network, naive Bayes, and so on. And so in today's class, we will briefly touch all of these in the hands-on side of the portion of the class. So if we look at the scikit-learn API that we have for the classification is again very standard and abstract. It has abstracted the different portions of tasks. So there's something called fit function, there is something called predict function, score function. So those are the regular types of function that you would usually use when building a classifier. And the unique type of classifiers that you want to call to build the classifiers would be specified by the different classes. So you may have like a neural network classifier, but again, its functions would still be same. Like you will have neural network, they would have a fit function, predict function, and a score function as the different functions within this particular class. I wanted to touch this portion called as categorical variables. So as we saw when we were building the model for classifier, we may have certain features such as a color, for instance, and the color of a flower could potentially be depicted like, or over here it is a garment. So over here, the color of the garment could be green, red, or blue, right? And we could potentially also have the size associated with it and the class associated with it. Now, when building machine learning model, we won't directly use these input features as is. We will have to do some kind of pre-processing so that they are converted into some integer values before they are passed to this classifier functions. So in this, you could have something called as nominal way of encoding. So in this, what happens is the green could be converted into a vector such as 1, 0, 0. The red could be converted into something like 0, 1, 0. Blue could be represented something like 0, 0, 1, right? Similarly, we could also denote M, for instance, as 1, L as 2, or XL as 3. Now, the difference between these two, the nominal and the ordinal, is that in nominal representation, there is no weightage associated with either of these values. Like there is no relation like whether the green is more than red or the blue is having more weightage than red, for instance. Whereas in ordinal, you do have some kind of relationship that goes like M the medium is less than the L and XL. So there is some relation associated with this. So there are different techniques for representing these values into integers. So one of them is called as one-shot encoding, and there are also so you must be thinking like, how do we convert all these values? So for small categories, this is fine. Like green, you could represent by 100, but if you have a lot of different kind of categories, doing them that manually is very tedious activity. Also, if there are a lot of different features types, like you could have like M, L, XL, and it could have more different unique entities, then how do you represent them? So scikit-learn internally has different APIs that will allow you to represent these like a string kind of values into an integer by doing some of the encoding things. So there are different techniques for doing that encoding. Over here, we saw nominal and ordinal. There is something called one-shot encoding, one-hot-shot encoding that we will cover in one of our next class. But over here, we can see that the green, which is represented as 100, how do we do the transformation is that green becomes an individual column in the input data set. Similarly, we have the blue, green, and the red. So these become the 3 additional columns for representing a color. So you can see that there is just one color column, but when you kind of encode that, we now have 3 additional color columns, and each of them represent the different values that are associated with it. So the green, the row 0 could now be represented as blue 0, the green as 1, and the red as 0. So that's kind of the encoding that is required when building the machine learning model, and we don't directly pass whether it's a green, whether it's a red or blue as a field. So it has to be encoded in some kind of integer representation. I hope that makes sense. If anybody has any questions. Okay. All right. I think that covers the slide part of it. Let me walk through hands-on Jupyter Notebook activity. So is the Jupyter Notebook visible to everyone?
Yes,
I can see it.
Okay, nice. So yeah, so we will be just covering the iris flower data set that we talked about. Again, all these data sets that we are covering are directly provided by the scikit-learn library. I've been saying scikit-learn because I think personally for me, it was very easy to get started with scikit-learn. And when I was working with the scikit-learn, that time Keras and TensorFlow were still in their initial stages. So I started with scikit-learn, but same techniques you can represent them in like Keras and TensorFlow, and probably in some of our next classes we will use say a Keras or TensorFlow examples. So for today's, again, we'll be just using the scikit-learn library. So again, over here, we can see that we can just call the data set and we can just load the data set, which is iris. Now, if we look at the data set, Then the feature names are again represented as sepal length, width, the petal length, and the width. So these are the 4 columns that we saw previously. And if we look at the target names, they are basically the categories of the flower that they belong to. So it could be Setosa versicolor and Virginica. So these are the 3 different categories. Now, if you invoke something called description, that will provide more description for that particular data set. So we can see that this particular data set has 150 different instances that are associated with each of the categories. And then we have attributes, 4 numeric predictive attributes and class. This just summarizes what is a mean max of those different features. Again, this is, we are not doing any like machine learning tasks right now, but this just provides the insights for each the data set that we are looking at. Now, the X or the input data set that we see can be represented as, if we call iris.data, then it will print all the 4 columns and the values associated with the 4 columns, the input data set, which is the sepal length and the petal length and the width. So all of these represent those input features. And if we look at the target, you will see the target is classified either as 0, 1, and 2. So if we look at this particular data set, it already has the encoding done for us. So the output, the target is not as Certusa or those versicolor, those categories, but rather those categories are represented as integers like 0, 1, 2. Okay, so it is, the encoding has been already done by the data set. But there are instances most of the time wherein this encoding is not done for us, and we'll have to do that by ourselves using some of the libraries that are provided, say scikit-learn or the other machine learning modules. So we just we assign the value, the iris data to X and iris target to Y. Now let's look at how we can do the classification based on the k nearest neighbor. So again, it's very standard. You can see that we are just calling like 4 lines to have a basic neural network, not nearest neighbor classifier to be built. We specify how many neighbors that we want. We specify, we call the fit function, and then we call the predict function. So that's how easy it is to just build a classifier. To the fit function, we basically pass the input data set, which is all those 4 columns, right? And the Y would be the encoding that is done, whether it's a 0, 1, or 2 for each of the rows. And once that classifier is built, we could pass an input to this classifier. We say that it's supposed to be 4, 2, 1, 1. So this is the sepal length, sepal width, petal length, and petal width, right? And if we pass that to this classifier, it will tell us whether, so the output of this would be either 0, 1, or 2, right? So that would be the output of that. And if we want to see, if we want to decode what that 0, 1, or 2 will represent, then that's what we are trying to do over here. Is basically we are trying to decode what the output is and to what category it associates. And we can see that the output that was predicted by them, by this classifier, belongs to the Setosa flower category. So that's a basic for getting the classification done in the KNN. But perhaps we also want to check what is the model accuracy for this classifier is. We could, as we had talked about in the previous classes, we could use something like a train test split mechanism provided by the scikit-learn, and we could have some training data set from this whole data set to train a model, and then we could have a test data set to test the accuracy of this model. So that's what this code snippet does, is basically we invoke the train test split data set, and we say that the test size is 0.33. So test size is 33% of that input data set. And so we have the 70%, or yeah. So we have the 1/3 as a test data set and 2/3 as a training data set. So here it just represents what are the dimensions. Then we call the classifier. Again, you can see basically in these 3 lines of code, we are building our classifier. We can invoke an accuracy score, which is another function that will let you know what is the accuracy of this classifier. Okay, so over here, the nearest neighbor, the K value for this classifier, we did set it to 1. And when we ran the accuracy, it came to like 0.96, which is like around 96%. But if we kind of increase the value of K to something like 4, then we see the accuracy for this particular data set. Now, it need not be the same behavior for other data set. It just depends on the data set. So for this data set, if we increase the number of neighbors to 4, then our accuracy increased to like 0.98. So that's just showing like how the value of K could affect or change the accuracy of the model. I'll be briefly covering like the different regression classes that are available within the scikit-learn. So over here, we have another regression classifier called as random forest. This is how one can invoke that. And we can see the accuracy again is 0.98. Again, if you want to see what is the output of for a given input value, then we can see the prediction is 0. So that would be our first category for that flower class. So this again represents how to call a logistic regression. And this is how one can invoke. Again, you can see that we call the fit function, we call the classifier method, and basically within 3 lines of code, we are building this classifier. This snippet over here talks about how we can use the decision tree classifier. Same thing, we are invoking like a fit function. We are calling the decision tree classifier. We can define the depth for this tree that we are going to be building. We can say that we would like to have a depth of 4. So based on that, the decision tree would just have 4 levels of hierarchy. And so those are things that we can define. I just wanted to represent how this decision tree would look like when it is built. So there are like methods to do that. So there is a function called as plot_tree within this module, which will allow you to see how that decision tree will look like. So over here for this classifier, we can see that it is based on this petal length. So if the petal length is less than 2.45, then we can say that the flower class belongs to the setosa. So the left is yes and the right is no. Okay, so true or false. So if it is false, then there is another decision that we have to, that it validates against. So it then checks whether the petal width is less than 1.75. If it is, then it checks another condition, and so on and so forth, right? If it is not, then it checks another condition. So that's how it just keeps on building. And I just wanted to show like how this can be represented on the Jupyter notebook for any different kind of decision tree classifiers. Over here, I wanted to show like what. Okay, so over here, I wanted to show like the different classifier regions that the model sees when we represent the different classes. So over here, we can see that there are three kinds of classes, and they are separated by this different decision tree boundaries. And the way one can build is something like this. And over here we have, I'm showing like plots for these different classifiers. Okay, but there is another plotting library called ML Extend, which already has a function called as plot decision regions, and it will show you the decisions, the decision region for this. So for this classifier, for visualization sake, there are two input features, which is the petal length and the sepal length. And based on that, there are these three different categories. So 0, 1, and 2. So that's how they are represented. And we can see how the different points are associated in in these different categories. So this is just for visualization purpose. One can invoke this plot underscore decision regions function. There is also another classifier called XGBoost, which one has to install manually. It's not part of the scikit-learn, but again, the invocation is similar. Okay, next I wanted to, since in the previous class we talked about normalization of the features. One of the questions was, do we really need normalization? What is the effect of normalization? So we talked about something called a standard scalar or min-max scaling for normalizing the different feature values, right? So over here, we'll see with an example how the normalization improves the computation accuracy or the computation speed for building this classifier. So in this example, when we are doing the logistic regression, we can see that we are not doing any normalization, okay? So we can see that after 114 iterations, when the logistic regression model was built, it took 114 iterations to build that model. Now, the same model, when we do the scaling, right? The min-max scalar for the input data set, we can see that when we use that scale min-max scaling, we can see that the regression now took just 22 iterations to build that model. So the accuracy is most likely going to be the same, but what we see the difference in this case is the computation speed with which the model was built. So you can imagine if you have a very large data set, then the computation time may be reduced if you use some kind of normalization technique. So neural network is also another kind of classifier I'm just going to show a snippet over here, but I think we will cover neural network and deep neural network in the coming classes, wherein we will talk in more details how to use the theory behind the neural network. But again, if we want to invoke something like a neural network, then again, the invocation over here, we just call this MLP, perceptron classifier. And this is how one can build neural network based classifier. All right, any questions so far? Okay. So I was thinking there is this homework that I wanted to talk about, since we have like 15 minutes or so. So I found this nice, so there is an online website, which I think we had mentioned previously, called Skaggle. So it's like a community wherein there are a lot of challenge problems, which comes with data sets for solving some of the real world problems. So it already has like data that is provided by this portal, and you have to build. So there are different challenge modules, and each challenge may be based on either regression, classification, and all sorts of new machine learning models. And in this, there is one notebook, a Jupyter-based notebook, that is hosted, and people also post different tutorials on this website. So it's very informative in that sense, that you can navigate this website, and there are also like discussions and courses to like ramp up quickly on the machine learning. So there is this one notebook that I have linked on the Jupyter, which talks about using classification for identifying handwritten digits. Okay, so let's look at an example over here. So we have a digit, for instance, like a 6, that is represented by an image. Now, if we want to build a classifier, so the input that we have over here is this image, right? And the Y, or the target that is associated with this image, is represented as, it is labeled already. So the data set that is provided by this is already labeled. So there are a lot of images, and there is also a label which says what digit that image represents. So we have image like 6. Okay, there is a handwritten, somebody has written 6, and somebody has manually said that, okay, this figure represents a 6 value. Okay, now if we want to build a classifier which will identify, if we provide any new image to this classifier, it will identify whether it's a 0, 1, 2, 3, and so on, right? So that's what we want to build. Then the question arises, how do we represent this image, right? So we cannot directly pass an image to a classifier. How would we pass an image directly to a classifier? So the way that it is done is, the images are usually made up of different pixels. So so for instance, over here, we could have an image. I'm not sure for this. So the image, it can be represented as like 28 by 28 pixels. So what do I mean by pixels? So this image over here, you can think of this image as a composition of small squares. Okay, so we may have a small square over here. Okay, so like that, there are like 28 squares on the x-axis and 28 squares on the y-axis. So the whole image can be represented as a grid of 28 by 28. Now, fine. So there are like libraries that are already available. So Python has libraries which can um, uh, take this image and represent it as a grid of say 28 by 28. Okay. So the next question is, we may have 28 by 28 grid. So what do we do next? So the way we we represent this is, each of these grid would have some intensity of either a black or a white color, right? So if we are representing this image as in a grayscale, then this square over here is like totally dark. Okay, and there might be another grid which is over here, which has some intensity of gray and some intensity of white. So at the end, we may be able to represent this image wherein each grid we associated a number of the intensity for that grid. Okay, and so at the end, that image, which is 28 by 28, can be represented as an array or a vector of size 28 by 28. And that 28 by 28 size can then be converted into a single row with 28. So basically do the transformation from 2D to a 1D dimension. And that becomes your one input feature, like one input for this image, and then you will have a label associated with that. So basically it would look something like an array like this, wherein each number represents an intensity for that grid. And then you will have a value like 6, for instance, which would be the target value that will be associated with this array. So yeah, I think that's what this Jupyter Notebook does. And it has, it uses some SVC, SVM kind of classifier, and does the building of the model, and you can then classify whether that image is represented as 1, 2, and so on and so forth. So that's what this exercise or the Jupyter Notebook goes into. So it would be interesting if you all could try this out before our next class. I have all represented that in the as a part of this homework. I've put a link to that Jupyter Notebook. Try importing that in a Colab, like a Google Colab. Try importing that code and try to run that, and let me know if you all have any questions on that front. Again, we will be posting all these lecture notes on this GitHub repository, right? And we'll be up. So just refreshers, like we will put all the schedule over here, and there would be useful links and video recording for each of the weeks, which you all can refer in offline manner. So any questions so far? I think that's what. Yeah, I think in next class we will we'll try to cover neural network and clustering machine learning technique. Any question, thoughts? Okay, if not, I think we'll end the lecture today, and hope you all have a good rest of the evening. Bye, everyone.
Thank you. See you later.
Thank you.
Thank you.
Thank you.
Thanks.